In 1961, American railroads were desperate. Hauling freight over the Rockies meant stringing together up to 10 underpowered locomotives, 160 pistons, 40 traction motors, and endless failures. In a move that rattled both engineers and the public, Southern Pacific turned to West Germany's Krauss-Maffei, the former tank builders, and imported 6 experimental hydraulic engines boasting double the horsepower of anything made in Detroit. These machines looked like engineering miracles, and on paper they were unstoppable. But when these mechanical superpowers met the airless depths of American mountain tunnels, their precision failed, their fluids overheated, and their systems melted from within. Why would the world's most advanced locomotive technology break down so catastrophically, and what does this forgotten experiment reveal about the collision of European ideals and American realities just beneath the surface? Shop foremen in the late 1950s faced a daily arithmetic that bordered on madness. To muscle a mile-long freight up a 2% mountain grade, Southern Pacific and Rio Grande crews chained together 8, sometimes even 10 diesel-electric locomotives. Each engine carried 16 pistons, 160 pistons on a 10-engine lash-up, hammering away hour after hour. Under the floorboards, 40 traction motors spun, each one a potential failure point. 10 separate electrical systems meant that any single glitch could bring the whole lash-up to a halt. Every trip over the Rockies meant a maintenance marathon. Mechanics spent nights crawling through engine compartments, swapping out burned fuses, cracked piston rings, and worn commutators. The shop logs from Roseville read like casualty reports: traction motors shorting out, crankcases leaking, turbochargers overheating. A single failed engine could delay an entire train, stranding crews and cargo for hours. The cost was not just in parts and labor. Every locomotive idled for repairs meant less power on the rails, more delays, and pressure mounting from executives desperate for efficiency. The arithmetic was brutal. Multiply every weak link by 10, and the odds of a perfect run dropped to near zero. In the boardrooms, the demand for a single, powerful locomotive grew louder. American builders promised improvements, but nothing on the market could break the 2,000 horsepower ceiling without risking catastrophic failure. As the freight loads grew heavier and the grades refused to flatten, the old solution, just add another engine, felt more and more like a losing game. The system was stretched to its limit, and everyone from the shop floor to the executive suite could feel it. In the high-rise offices of Southern Pacific and Denver and Rio Grande Western, patience was running out. Boardroom tables filled with charts and cost projections, all pointing to the same conclusion: the American locomotive market had hit a wall. General Motors and General Electric kept promising breakthroughs, but nothing left the drawing board with the muscle these railroads needed. Every proposal topped out at 2,000 horsepower, maybe a bit more if you believe the salesman. It was not enough. Not for the Rockies, not for the future. Executives studied the numbers and saw a simple equation. If one engine could do the work of 10, the savings would be enormous. Fewer crews, less fuel, less downtime. The maintenance logbooks from Roseville and Denver told the real story. Too many moving parts, too many chances for something to go wrong. The board minutes from 1959 and 1960 show the mounting pressure. Stockholders wanted higher profits, shippers demanded faster delivery, and the competition was sharpening its knives. Sticking with the status quo meant falling behind. With no domestic builder offering a true 4,000 horsepower locomotive, the search went global. European trade journals landed on the desks of American vice presidents. The name Krauss-Maffei kept coming up. German precision, post-war engineering, and a reputation for solving problems others could not. Their ML4000 promised more than double the power of any US engine, and it did it with fewer moving parts in the drive system. The board saw a way out: import the future, even if it meant turning to a company once known for building tanks. The decision was not made lightly, but the logic was hard to argue. If American industry could not deliver the horsepower, maybe Munich could. The order was placed. 6 machines, each a rolling experiment, were set to cross the Atlantic. The stakes were clear: bet big on foreign innovation, or get left behind by the very mountains that built the West. Underneath the streamlined shell of the ML4000, the source of its power waited in twin rows of cast iron. Each locomotive carried not one, but two Maybach MD870 V16 diesel engines, each a 16-cylinder, 4-stroke masterpiece, bred for speed and stamina. Together, these engines produced a combined 3,540 horsepower, nearly double what the best American diesels could manage at the time. The layout was tight, almost surgical, with every component designed for maximum output in the smallest possible space. Instead of spinning a generator to make electricity, the Maybachs drove directly into a Voith L630 hydrodynamic torque converter. This device worked less like a clutch and more like a river in a box. The engine spun a pump, flinging oil at high speed against a turbine. The force of the fluid alone turned the output shaft. There was no metal-on-metal connection, just liquid energy, channeled and controlled. That setup allowed for massive torque at low speeds, perfect for getting a heavy train moving without burning out traction motors or frying wires. The torque converter itself was the size of a compact car, bolted to the engine block and filled with special oil engineered to withstand extreme pressure and heat. From there, power traveled through a set of thick steel cardan shafts, the kind you would expect to find under a heavy-duty truck, not a locomotive. These drive shafts delivered every bit of the Maybach's force straight to the wheels. The result was a machine that, on paper, could do the work of 3 American engines with a single coordinated punch. For the engineers who designed it, this was the future of railroading: fewer moving parts, less electrical fuss, and more raw power delivered directly to the rails. Hydraulic drive wasn't just a clever engineering trick, it was a different philosophy. American locomotives used electricity to move power from engine to wheels, but the Germans trusted fluid. Inside the Voith torque converter, oil became liquid muscle. When the engineer pushed the throttle, the Maybach engine spun a pump, hurling oil at turbine blades. The result was a rush of torque, delivered smoothly, with no gears to grind and no wires to burn. If the wheels started to slip on wet rails, the fluid simply spun faster, absorbing the shock. There was no risk of a traction motor frying itself or a fuse blowing out. The whole drive system was a closed loop: engine, pump, oil, turbine, driveshaft, wheels, nothing wasted, nothing lost to electrical resistance. This design allowed for an almost surgical control of power. On paper, the ML4000 could crawl a heavy freight up a grade with less drama than any American diesel electric. The Germans built their transmissions to such tight tolerances that even the oil had to meet exacting standards. In Europe, this precision paid off. Railways ran on time, and hydraulic drives rarely failed. But that precision came with a hidden cost. The system depended on clean oil, stable temperatures, and a predictable environment. Outside the lab, in the wild American West, those variables were anything but predictable. The same fluid that delivered perfect traction on a rainy day in Bavaria could turn into a liability when the mercury climbed and the air thinned out in a mountain tunnel. The promise of liquid muscle was real, but so were the risks that came with it. On October 31, 1961, the Port of Houston turned into a stage for something the American railroad world had never seen. 6 locomotives, each longer than a city bus and clad in curved silver shells, rolled down the gangways from their transatlantic freighter. Dock workers paused, cranes idled, and a crowd gathered along the fences: railroad men, local reporters, curious families. Headlines that week ran with phrases like German power and super locomotives. There was no mistaking the symbolism. These were not just machines, but imports from a company whose name still echoed with the memory of wartime industry. The Krauss-Maffei badge on their flanks drew as much attention as the sleek rounded noses and turret-like cabs. To American eyes, they looked less like trains and more like futuristic weapons, something out of a European science fiction serial. Photographers crowded the rails, snapping shots as engineers in crisp uniforms stepped out and conferred with Southern Pacific officials. The press jostled for interviews, firing questions about horsepower and reliability, and about the wisdom of turning to a former adversary for help with America's toughest railroads. The spectacle was equal parts marvel and suspicion. For a moment, the technical details faded behind the sheer audacity of the scene. German-built engines, fresh off the boat, and ready to take on the wildest terrain in the West. The promise was clear. If these locomotives could deliver on their reputation, the old arithmetic of 10 engines for every train might finally be history. First runs on the Texas plains delivered exactly what the Southern Pacific Board had hoped for, and more. The ML4000s lined up at the head of mile-long freights, engines idling with a low, confident rumble. Engineers reported a new kind of quiet in the cab, no high-pitched whine from traction motors, and no flicker of warning lights from overloaded circuits. With the throttle wide open, a single German locomotive hauled loads that once demanded 3 American diesels. On flat land, the numbers were impossible to ignore. 3 ML4000s replaced 8 F7s, matching the same tonnage with fewer moving parts, less fuel, and a single crew. Management watched the early results with growing excitement. Trains pulled out of Houston and San Antonio yards, accelerating smoothly under the hydraulic drive. Shop foremen noted a drop in nightly repair calls. The hydraulic transmission absorbed the worst shocks of heavy freight starts, no scorched wiring, no burnt-out motors, just the oil churning through the Voith converter, cool and steady. For the first time, it seemed the arithmetic of American railroading was about to change. The confidence spread quickly. Reports from the field described the German engineers as meticulous and almost proud, riding along with notebooks in hand and recording every vibration and temperature swing. Southern Pacific management assigned the new engines to longer, heavier trains, pushing the limits of what a single locomotive could do. The success on the flats was undeniable. The next step was clear. Send the ML4000s west into the mountains and see if German engineering could finally conquer the grades that had humbled every American design before. The first time an ML4000 entered the Moffat Tunnel, the crew braced for a slow crawl. 6 miles of blackness, a 2% grade, and nowhere for the heat to go. At 10 miles per hour, the locomotive acted like a piston in a cylinder, pushing a wall of air and exhaust ahead. The tunnel ceiling trapped the exhaust at 800 degrees, rolling it backward until it found the worst possible target, the air intakes on the roof just behind the engines. Instead of cool mountain air, the Maybach engines inhaled their own fumes. Oxygen dropped, combustion faltered, and the engines lost power even with the throttle wide open. The cab filled with the sharp sting of diesel smoke. Red lights blinked on the dashboard, first oil temperature, then transmission pressure. The Voith hydrodynamic converter, now starved for airflow, began to cook its own fluid. Crew logs recorded transmission oil readings climbing past safe limits. The special hydraulic oil, engineered for Bavarian summers, started to thin and to bubble. In some cases, it flash-boiled, filling the gearbox with vapor instead of liquid. The drive system, designed to be a closed loop of liquid muscle, turned into a pressure cooker. As the heat spread, another weak link failed. The control system relied on air lines made of rubber and plastic, routed through the hottest parts of the machine. With tunnel temperatures climbing, the pneumatic logic faltered. Air pressure dropped. Valves stuck open or closed. Engineers reported brakes refusing to release and throttles locking in place. In the worst stalls, the locomotive simply shut down. Darkness, silence, and the hiss of cooling metal replaced the roar of the engines. Crews waited for rescue, breathing the same hot, greasy air that had just killed their machine. Some had to be towed out by American diesels, their faces streaked with sweat and soot. The promise of German engineering had collided with the reality of the American tunnel, and the result was a chain reaction that no one on either side of the Atlantic had predicted. The first ML4000 to stall in a tunnel was just the beginning. Once the airlines melted and the engines choked, the consequences rippled through every corner of the railroad. Mechanics scrambled for replacement parts that had to cross the Atlantic by boat, each shipment delayed by customs and paperwork. A single failed pneumatic valve could sideline a locomotive for weeks, while the rest of the fleet limped along, one overheating run away from disaster. Shop crews grew frustrated. The Maybach engines demanded surgical precision, but American rail yards were built for speed, not delicacy. Tight tolerances and metric bolts clashed with the brute force reality of mountain railroading. Every breakdown meant hours lost in translation, between languages, between engineering cultures, between what worked in Munich and what survived in Roseville. Costs soared. Every hour a German engine sat idle, the savings promised in the boardroom vanished. Southern Pacific's maintenance logs filled with notes about fluid leaks, warped panels, and air compressors that would not hold pressure. The pneumatic cascade, one hot tunnel, one burst line, and suddenly the brakes, throttle, or even the horn would freeze. Crews lost faith. Dispatchers started assigning the ML 4000 locomotives to flatter territory, hoping to avoid another mountain shutdown. But the reputation was already set. The experiment had become a liability. Competitors took notice. EMD and GE engineers, once skeptical, began working overtime. Within 2 years, the SD-45 and U-25B rolled out of American factories, locomotives that matched the Germans in horsepower but used proven diesel-electric systems. The market shifted overnight. Orders for foreign hydraulics dried up. By 1968, nearly every ML 4000 had been cut up for scrap. Their cardan shafts and Maybach blocks sold off as curiosities. Only one survivor remained, SP9010. Pulled from a weed-choked siding and restored by volunteers in California, it stands as a monument to both ambition and miscalculation. A machine built for a different world, brought back to life by hands that never forgot the promise of liquid muscle. Today, American railroads still measure innovation against the landscape, not just the lab. When foreign solutions collide with local extremes, the lesson endures. Engineering brilliance means nothing if it cannot survive its environment. As we chase new technologies, hydrogen, batteries, and automation, the Rockies still ask the same question. Can you handle the heat? Share your thoughts below.